Good decision, because today's lecturer, Lawrie Virgin, I'm going to tell you some things about him. His field is nonlinear dynamics from various points of view, certainly numerical chaos, things like that, and then in terms of applied subjects. I've made a note. He did applications, among other things, to rolling of ships to avoid capsizing, aerodynamic flutter, aeroelastic flutter, I mean, if panels that are being forced by the wind or whatever. Solar sails, very thin structures. He's written 2 books. One of them called Introduction to Experimental Nonlinear Dynamics. And there's a combination for you, Experimental Nonlinear Dynamics. Vibrations of Axially Loaded Structures. Those are 2000 to 2007. He was educated in England, and finally he went to Manchester and Cardiff for his early degrees, and finally the University of London, which he graduated PhD in 1986, which I mentioned the dates because many of you are thinking about what you will do for employment once you graduate. In 1988, he was at Duke, and so he has basically been at one university for his whole career. But he was just explaining to me that as an undergraduate, he had a scholarship to the United States, and he went to UIUC, Illinois, where by amazing coincidence, he shared an office with Tim Healy, who was at that time a graduate student there. We don't understand these things, but it's all there. And now at Duke, he is in several departments. He's actually in the Department of Mechanical Engineering and Material Science, but it was just a few years ago when I visited, he was the chair of the Civil Engineering Department too. In any case, we're very lucky to have him fight all of this weather and come up and talk to us, and you can see that he's going to speak to us about very slender structures. Thanks.
Well, thank you, Richard, and thanks for everyone for showing up, because the weather outside is amazing, isn't it? You guys braved it, so congratulations. So it's always a pleasure to come to Cornell. It's 40 years, almost exactly since I first came to Cornell. I always enjoy coming back. So today, so I'm really an experimentalist, but a lot of what I do is informed by mathematics, whether it's bifurcation theory or ODEs, PDEs, linear algebra. And so what I'm going to talk about, I think, is appreciable to a general audience, which Colloquium should be, right? Not terribly specialized. Got some little models that we can play with a little bit later. Mechanics of very slender structures. Let's get this started. A few people to thank. There's a Virginia Tech professor who Andy over here has worked with as an undergraduate, who I've worked with for 35 years or so. A couple of PhD students who have now graduated, and Elliot from Cornell, shortly to be at the University of Chicago as a postdoc. That's not a very up-to-date photo. Sorry about that. Sorry about that. All right. So very, very slender structures. And you know, I realise you're not structural engineers, so I'll be fairly gentle with the introduction. But here's some practical examples of very slender structures. So what I'm primarily going to talk about is structures where their weight competes with their elastic stiffness. Okay? So this is actually from North Carolina, believe it or not. This was a tree that suffered during an ice storm. So we may have had some freezing rain this morning. So rain that falls as liquid but touches the surface of something and freezes. And of course it's too heavy, and this buckles over. This is some nice sunflowers, which I think they've been genetically alterated in order to have a nice big flower head, but the stalks can't actually stand up and they droop down. That's a giant redwood in California, which I've never seen, by the way. You probably I would love to go out there and see them. They can be 110 meters high. Imagine that. And of course, 100 years ago, many of them were wiped out by lumberjacks. Does anyone recognize this character? He's called the Magnificent Bellow, and he was the main clown with Barnum and Bailey's circus. And one of his acts is he would climb up this pole. That must be some sort of fiberglass pole. He called it a lamppost. And then he would get on the top of it, and it was very, very carefully designed such that it was right on its critical buckling point. So if he stood up, it would droop over. If he crouched down, it would stand up. And then it would bend over onto the audience, and all the little kids would scream. It was very exciting to see. He was really using mechanics, very near a critical buckling load, although he probably didn't realise that himself. And little girls can get badges when they're in the brownies to show that they've been to the circle. Richard mentioned solar cells, so these are these massive kite-like structures that NASA's been developing for the last 20 years or so. And the idea is that they're very convenient for deep space propulsion. They're just propelled by the photons from the sun. So you don't have to carry any fuel or anything. And what makes them work is that they are a massive expanse of very light material. So when I say a massive expanse, a kilometre square. So it's essentially a kite, but it's not propelled by the wind, it's propelled by the sun's photon. And my interest in this are the spokes to keep the thing unfurled. So think of an umbrella, right? It's the material of the umbrella that keeps you dry, but it's those thin spokes that keep the umbrella unfurled. They need to be lightweight, right? You don't want a heavy umbrella. They need to be relatively stiff, otherwise the thing will collapse. And then there are other examples like marine risers. I'll talk briefly about this in a minute. And DNA, lots of examples of biomechanics, which I don't really do, but there are good examples. All right, bouncing goats. I put this in my abstracts, right? In fact, you asked me about this. So this is a video. Let me just play it. This is real. There's nothing sort of deep faked about this. It's in France. It's in some field in France, and these goats apparently do this all day long. And this is a billy goat, and he's just bad-tempered. He just tries to headbutt everyone. Look, and he tries to get the others off. He's just foul-tempered. But these other ones, they climb on and they bounce, and they slide off, and they try and get it going. They're trying to resonate the structure, right? They're trying to excite the natural frequency, the dominant natural frequency. And in terms of mechanics, this is a semicircular arch. It's got pin support here, and I will return to this later. But they're having a great time. And can you see when there's all three of them, the natural frequency has dropped down? It's sluggish. That's because it's less stiff, effectively, as well as the mass being greater, of course. So you can watch this, and they do this all day. And that is a slender structure. So what I'm going to do is, for this talk, I'm going to look at 4 representative structures and just, draw out 1 or 2 interesting facets of them. So 4 representative structures. Each one is sort of oriented upwards, because if you, what I'm going to do is increase their length. And if they were just drooping down, it wouldn't be terribly interesting. But if they're oriented upwards, they often suffer a bifurcation, right? They buckle. So here they are. And of course, if you have a bar, and I can demonstrate this, if you have a bar that's very long and slender, then it really acts like a chain. In other words, the flexural stiffness of the material is relatively negligible compared to just the weight that's causing it to be almost like a pendulum. And we'll look at that in more detail. And then just other configurations. Now, for those of you who are not familiar with this, we use ordinary differential equations and sometimes partial differential equations to model simple cantilever dynamics. So here's a cantilever. And if I clamp that at one end and push down on the other end, it deflects by a certain amount. It's very straightforward to work out what that is. It's a linear, it's because the curvature of a flexural member is related to the bending moment, Anyway, if you push on the side, it deflects and it's nice and simple. Similarly with vibration. So if I just clamp this and pluck it, it vibrates. It's very simple. And with buckling as well. So if I was to clamp this, push it down, it reaches a certain magnitude of load and it would buckle, which is a bifurcation. It's actually a supercritical pitch fault bifurcation for those who know about that stuff. Okay, but that only works, really, if you do have a trivial equilibrium solution. It starts off straight, and the deflections are small, essentially. Well, it doesn't take much deflection for this to be violated. In that case, it's much better to use what are called arc length coordinates. And this is a, well, I'll show you the PDEs in a minute, but that's more difficult to solve, but you can. In my work, we solved this as a, using the shooting method. You guys familiar with that? Where you know certain conditions at one end and you solve the equations and try and satisfy at the other end. So, these are those elastic equations. I'm not going to dwell on this, even though this is a CAM seminar. But basically, we've got a bunch of ODEs, PDEs. And what's different, I would say, about this work than a lot of other work is weight, this W, weight, and I'm going to non-dimensionalize it in this way. So weight is an important factor which we usually ignore. We can take this set of dimensional equations and non-dimensionalize them, and I won't dwell really on what these mean. But the point is you can then solve this as a boundary value problem, and of course Mathematica is the way I do it. I'm not particularly interested in specific solution techniques, but use an ND solve and find it in Mathematica is a great convenient way of doing this. Then you can consider small vibrations. So you can take a structure that is not now restricted to small deflections, it can do anything. And now we're also going to look at vibrations about that highly deflected configuration, if it's there. So you consider small oscillations about equilibrium, where equilibrium is given by the solution of this. And then you can use the Shooting method again to essentially solve for the natural frequencies. Right? So you solve for the shape, and then the natural frequencies about those shapes. So let's go to our form. A drooping loop. Now, it's funny, when I was given the information about this seminar, I was given some information about, it's a general audience, right? So don't be too specific when I'm saying this. And also, try not to use slides. How about using the chalkboard? Well, I can't do that because I have lots of videos. But I have some demonstration models. So this is the drooping loop. And I use this in my classes, and the students quite like it. So what we have here is a rod. So Andy, this is what I was saying. This rod is like a steel coil with a rubber coating. So it's a bit like a bicycle brake, but it has some interesting properties. So what you can do is come up with a system like that. Let's call that the trivial equilibrium solution. And so I'm going to base this purely on energy, right? Potential energy. So let's do the following. Let's use as our control parameter the length, the arc length, which I can push material into. And then we're just going to use that deflection, the lateral deflection, as our variable. So look what happens. That's trivial, that's stable, right? Stable, small perturbations. But as I go up higher, you notice the natural frequencies are getting lower. It's becoming less stiff. And if I go up high enough, it does that. Well, that's stable, right? And that's stable as well. This has lost its stability, it won't stay there. So without doing anything, let's just think about the equations that might govern or tell us what's going on. And that is what I'm claiming is the equilibrium solution. Wow. Q is this lateral deflection. We've got a bias parameter, I should really have mentioned that. If I feed material into this from the bottom, every time it goes the same way, right? Because the symmetry is broken. So in bifurcation theory, we like to have a symmetry breaking term, and that's epsilon in this case. And so this is what you have. I feed material in, it gets to this point, that's a saddle node bifurcation, and it snaps to this highly deflected configuration. But there's also this other solution on the other side. So, what's going on? Well, do you recognize this, anyone? It's a butterfly catastrophe. Have you heard of that? So in bifurcation theory, there are certain generic forms, and of course that's just 6 factorial, 4 factorial, but that's the potential energy that's governing the behavior of this. So it's a 6th order, it's odd, other than this small bias. It's a 6th order polynomial. The equilibria configurations are from the first derivative equal to 0. You see that will actually give a constant term there. And if you plot the bifurcations in a plane of the control parameter versus the initial deflection, you get this butterfly shape. Alex, have you seen that before? And so it depends where you are in terms of this parameter space, you get different forms of potential. And so this is what that shape looks like. And when I was playing around on Mathematica, I found a way of having these surfaces as translucent. So this, you can see this double cusp, this very interesting butterfly shape is exactly this. And then I 3D printed it. So I'll hand this around. So essentially those bifurcations are where the second derivative of the shape hits 0. That's their critical point. But I haven't really solved anything, have I? I've just looked at the form. And now you can solve this using the Elasticity equations.
Coordinates are mu, epsilon, and q.
Yes, exactly. Yeah. And you have to sort of orient it, figure out which is which. So you can solve this using the Elasticity equations, and you can take data, and I did all that. I just wanted to use this as a demonstration example to set things up. What's sort of more interesting in some ways are these. So this is a standalone column. So if I ask you the question, how tall can a column grow in a gravitational field before it just buckles under its own weight? And the answer is that. Where this is weight, flexural rigidity, Young's modulus, second moment area, and that was formed by Greenhill in 1881. Sommerfeld in 1905 noticed that if you have a mass on a rod and you turn it upside down, those natural frequencies are a little bit different. Minion Theory says that they're not, right? Minion Theory says that they're the same. And there's an interesting exercise you can do where if you make this, rather than what we call a prismatic beam, if you make it tapered, so think of an aircraft wing, right? It's thicker at the roots and thinner at the tip. And you optimize that system for a tree, for example, you find out that there's this natural 3/2 power law in terms of the radius for a tree, and it's exactly what the Eiffel Tower was designed at. Right? That's just using gravity as a supremacy. Other thin, slender structures, that's my cat. Whiskers, axisymmetric, right, circular. And her favourite toy is actually a peacock feather, which is also a slender structure. And you see there, she's actually exceeded the yield strength of the material. That's not what I'm doing. Everything I do is elastic, but that can happen if you overstress. One other thing I'd like to show with this, and again you have to know about bifurcation theory, is that when this structure buckles, this, so if I feed material up, right, and it reaches this point, it buckles completely. So that's a subcritical pitch fault bifurcation. And if I then turn the system around and do it again, it also buckles, but at a different place. That's because it's imperfection sensitive, right, which is the standard theory in bifurcation theory. However, the subtle node is not. So what do I mean by that? So it's buckled, and then I take material up, and look what it does. It stands to attention. And if I turn that around and do the same thing again, does it at pretty much the same length. There's a subtle node bifurcation which is not imperfection sensitive. So that's a demonstration of that. And the reason why imperfection sensitivity is such a big deal in practice, so cylinders, axially loaded cylinders, are notoriously imperfection sensitive. So NASA, this is NASA Marshall, I believe, have a lot of problems designing their solid rocket booster tanks because they want to make them as lightweight as possible, right? Which is the payload. But they're very sensitive to small geometric imperfections. So this is a plot. I know it's not very clear, but this is essentially the buckling load versus some geometry. The radius divided by the thickness. And NASA did masses of tests over the years and plotted them all. And so if you have a particular geometry here, the buckling is all over the place, like 50% spread, even with really careful experimentation. And the reason is it's imperfection sensitive. Okay, I'm going to take a slight little detour here. So I'm going to talk about a cantilever. So take this cantilever. So if I grip it and I pluck it, it's got a natural frequency. And what does that natural frequency depend on? It depends on the length, it depends on the cross-sectional properties, it depends on the material, and that's a standard result, like this. Of course, there's an infinite number of frequencies, but we're really interested in the fundamental. So this is just a number. This 2 pi is to put it into hertz, the length squared, density. So the frequency of a cantilever scales with the inverse length squared. And you can sort of non-dimensionalize and show it's a straight line. So if I've got a cantilever like this, and I want to halve the natural frequency, what would I do? Make it square root 2 longer, right? So that's fine. And some of you may have seen this. I started thinking about this. So this is what I call sympathetic resonance. So this is a set of, I think there are 16 cantilevers grouped into 4 different lengths. And if I pluck one of those, the other 3 at the same length vibrate in sympathy. So what's going on? Well, it's resonance. There's a tiny amount of energy that gets transferred through this base from this to the others. And because it's resonance and it's very lightly damped, you get this massive magnification. And it's true for the others. So if I pluck this second longest one, it's actually difficult to see, I bet in the darkness, but I'll hand this around, don't break it. Of course I can 3D print another one if you did, but if you pluck one, then the others at the same length vibrate in sympathy. And that's all 3D printing. And then you can do things like this. This is 15 identical cantilevers, but they're grouped into 3 groups of 5 cantilevers according to their thickness. And I've just painted them on the end so you can see this. So if I pluck a pink one, the other pink ones are the same thickness and in the same natural frequency, resonate simply. And then this is the last one I did for that. And I thought, well, there's nothing special about a cantilever, is there? Let's make it a bit more interesting. So I printed one with some turnarounds. And again, if you pluck these, it's the ones of the same length that then vibrate. So it's a bit like a tuning fork for the musicians amongst you. It's a very similar principle. And with this one, when I got the technician to print it, it ran out of material halfway through the print. I don't know if anyone's done 3D printing. And when he put the new cartridge in, instead of putting a black cartridge, he put a yellow cartridge. But it's actually very effective, right? I mean, it's one of those things where it actually looks better because of that mistake. Anyway, they're not terribly slender, are they, those structures, but it's still interesting. Okay, and those are just videos. And since I'm actually handing around the demonstration, I don't need to do that. So this is the main point of my talk, really. So If I have a short cantilever, this is just representative of any structure. If I change its orientation like that with respect to gravity, it doesn't change, does it? In terms of its bending, its flexion. And indeed, natural frequency doesn't change. What if I have something like this? Or, even worse, something like this, if I increase the length. Right? So that's buckled, that's post-buckled. And now, as I change the orientation, it does have a big effect on the frequency. So let's look at that. Let's look at that. So firstly, this is the linear theory, right? So I said that the cantilever frequency scales with the inverse length squared, so it tails off. But then let's look at two other orientations, where the beam is just down and where the beam is up. Well, when the beam is hanging down and you increase the length, this is what happens. It just goes. And what it settles down to is a chain, right? So in that case, gravity is completely dominating elastic stiffness, and you can actually solve that using Bessel function. Conversely, if you have it oriented up and increase the length, it does this. The frequency drops to 0. It buckles, right? It buckles at this critical value. So if you're in an intermediate range of lengths, you can see you get a difference in the natural frequency according to the orientation. That's not in the linear theory. The linear theory just says it doesn't matter what the orientation is, you just have a natural frequency. So I went to the lab a few years ago, and I, with a PhD student, set up this experiment. So we got this long, thin strip of polycarbonate, and bolted it to a shaker, and put 30 targets, and used our laser to take data from all 30 targets as this was being shaken. And we shook it with random noise and sine sweep and all that stuff. And this is what we got. This is a fast Fourier transform that brings out the frequency content, and there are 30 superimposed. So the data from each of these has been superimposed in terms of its frequency content. And that's fine, right? They all line up, the natural modes. But what's interesting is if you then orient this vertically. So now, essentially what's going to happen is that gravity is tending to compress that one slightly. Gravity is tending to stretch that one slightly. So the stiffness is changing. So you do the same thing. You vibrate this and you take data from all 30 and you superimpose, and this is what you get. And at first I was kind of disappointed because they looked pretty, well, you can see some stuff going on here. But then you blow this up and look, you've got two distinct peaks according to whether it's up or down. And it's true for the other higher modes as well. And then you can do things like you can attach the ends of these with cables and do all the same sort of stuff, and you can see you get this mode split. So there's an effect of gravity or weight on the dynamics of the structure.
Lawrie, how are you driving it? Are you sweeping it, or you put white noise, or does it matter?
It doesn't really matter, as long as you excite a broad range of frequencies. We'd actually do both. Sine sweeps, chirps, random noise. So let's look at our third one, curved rings. And so, again, this is something that you can 3D print. So thin, and the linear theory says, well, what happens if what's the stiffness if I just do that or that? And that's a standard result. But what happens if I don't want to break it, but if you really go to extremes? You can use the Analytical equations to solve that, and this is what we did. So here's the linear theory. Timoshenko or Rourke's formulas for stress and strain, some of you might recognize that. And so for small deflection, this is non-dimensionalized, the force deflection relationship is linear, but not for long. It actually has this interesting behavior according to whether you're pulling or pulling. And when I was thinking about this, I was actually a while ago in a museum. This is a transport museum. See that bumper? Right? So it's actually an elastic ring, so when a vehicle bashes into that. And it's actually on Madge. Now, who has kids here? Not many. But Thomas the Tank is a popular kids program, and there's this bumper based on this elastic deformation. One thing I've been looking at recently is 3D printing. You can print any sort of geometry you want. So I've been doing some work on shock absorption, where you drop a mass onto an elastic component, and then it deforms, contacts the next, and so on. And there are advantages in terms of reducing the acceleration nicely and doing that. But let's go to the heavy case, or the slender case. So if you start with a stiff elastic ring, it doesn't matter if it's suspended from here or down here. It's a circle, right? It's a circle. But if you increase the length and keep all the other parameters equal, it starts to pancake out if it's oriented like this, and it starts to droop if it's oriented like that. And it all depends on this non-dimensional parameter. So you can think of this as really the force, the weight, force due to its mass, and its elastic stiffness, and how they compare. So let's look at this more closely. No, actually, let's do this. Here are some numerical results. And they sort of look right, don't they? They look right. And these are for different slenderness, this one non-dimensional parameter. So I went to the lab, did the same thing. Can you see the way it pancakes out? Obviously, we're in the gravitational environment in the lab. And it can actually buckle in on itself like that. When you suspend it from the top, it droops down like that. And so if you take data, which are these red dots, and you compare it to the Elastica equations, you know, the PDEs that we solve using the shooting method, they're almost exactly on top. That's for static deflection. This is for the lowest vibration frequency. So here's an example from the lab, and we measure things using a laser, which is great, right? Especially for lightweight structures, because you don't really want to touch them if you can help it. And so this is a laser in my lab, and this strip happened to be 3 inches wide, right? And let me just say something about units. I use SI units almost all the time, right? But NASA and the Air Force, who sponsor most of my research, they like old-fashioned units. So my question, this is a little quiz. How many countries in the world use old-fashioned English units, even though the English don't use them? What are the 3 countries? Come on. I'll give you that one. What are these other 2 countries?
Myanmar.
Yes, exactly. Myanmar, which used to be called Burma, and Liberia. They're the only 3 countries that consistently use old-fashioned units. The reason I mention that is because this is 3 inches wide. Before I was using 1 inch wide, right? So those results for 1 inch wide strips. I've gone to 3 inches, and this is what we get. Now I've got a bit of a story about that involving Elliot here, because he took the data. So I don't know about faculty here, but do you have to take courses in responsible conduct in research? Sort of financial management and treatment of graduate students. Can you imagine? So I had to go to this course, not because I was punished, but we all had to. And the provost was talking about how you should treat your graduate students well. You should, you know. And someone says, well, can you give us a case study, an example? And the provost was female. She said, yeah, there was one example recently where a Duke medical school professor literally locked his graduate students and postdocs in the lab overnight and refused to let them out until they came out with some good data. And I was laughing, I was thinking, is that wrong? Is that wrong? Anyway, the reason I mention it is because Elliot here in my lab took this data. And this, don't forget, is for the 3 inch wide strips. So he gave me the data, you remember this, Elliot? And I plotted it. And I was expecting nice smooth curves all the way. And then there was some sort of weird things going on here, which was kind of a mystery. So I plotted the data non-dimensionally, and it seemed to follow, these should collapse onto one curve. And at this point, there's something different happened. So, I plotted the frequencies, which Elliot also acquired. I noticed there are a few sort of weird kinks in this data. So I plotted that non-dimensionally, and it got the result. In fact, this was the result for the 1-inch strip, right? The mode changes, but don't worry about that. But then there was this kind of weird intermediate range in which there seemed to be a new frequency relationship. So what was going on? Well, this is what was going on. It turns out that there were coexisting equilibrium configurations like this and this. These have exactly the same properties, the same arc length, the same width, 3 inches, same thickness, same material, but they both existed at the same time. Right? Completely nonlinear. Right? A linear system has a unique solution, and that's it. So what happens is, you can take the system in one of these configurations, and you can tap it, and it settles down somewhere else. You tap it again, and it might... Anyway, I'll show you the video. So this first one, it popped down to a different equilibrium configuration. And then I tapped it again, and it popped up. Tapped it again, so it was doing this. And that didn't, that stayed, that stayed. And now it did pop up. So coexisting equilibrium configurations where everything else is the same. And if you've been trained in linear theory, you know that a small perturbation determines stability. Well, this is where the perturbation is not very small. It's more of a significant. And if you change the parameters like this one, this is a video, you can actually make it collapse. Does this remind you of Ray's stuff? And that didn't happen with the 1-inch wide strips, so why not? So clearly there is some sort of what we call a Poisson's effect. So if you take like a square sheet and you bend it in one direction, it has a tendency to bend slightly in the other direction. It's called anti-plastic bending. So to actually take a cube of material, if you squash it from one direction, it tends to expand in the orthogonal direction. That's Poisson's effect, and that's really what's going on here. So that is, strictly speaking, a plate. Right? It's a floppy plate. It's not really a floppy beam. It's too wide for that. Okay, and then just the last configuration. This is a pinch loop, and I like this one because, in terms of testing, it's one boundary condition, isn't it? It's clamp to clamp. It's like a clamp to clamp beam, but it's actually the same physical location. And in some ways, it's a bit like a cantilever, isn't it? But it's more interesting than that. So you can solve that using the Elastical equations. So this same important non-dimensional parameter pops out. These are the equations. What's different about this? Instead of just up, horizontal or down, let's make the angular variable beta. And you can see where it comes into the equations of motion. Right? So that's the orientation with the horizontal. And you can take data, and again, experimental data, theory. Similarly, the end point, the way it droops as you increase the length. Theory, experiment. I mean, it should be quite simple, right? Because geometrically it's not terribly complex, but it is highly nonlinear. You can do experiments on vibration. This is an experimental. So the first 4 natural frequencies are quite distinct. This is a lightly damped system. What do you think that little bulge is there for those who have done testing? So even though everything is in the plane, it's very hard to stop like a small torsional vibration coming in when you excite a system, and that's an example of torsion. So you do that, and you plot the first 4 natural frequencies as a function of length, and this video gives a couple of examples. So that frequency is that data point. Similarly, that frequency is that one. So it's like a sway, bounce, and of course there are an infinite number of them. But with the shooting method, based on those PDEs and solving for the natural frequencies, you can get them quite nicely as a function of length, and they agree with experiments. And this is an example of some natural mode shapes. So this is actually video, but it's not very good quality video. But can you see what it's doing? That's a sway. That's the lowest natural frequency, a sway from side to side, which I just demonstrated. And that changes with length. So if I have like a tightly, that frequency is quite high. And as I increase the arc length, it gets lower. And it gets lower in this, well, the previous plot. It gets lower in this characteristic sort of 1/L squared way, just like a cantilever. It's more complicated. And then this is the fourth mode. Sorry, the resolution isn't very good here. But it's doing this. It's like a breathe-in, bounce-in, but not the simple one. It's the fourth lowest natural frequency. So let's look briefly at this orientation. So when you have something that's hanging down, if it's a short arc length, say here, you pluck it doesn't really matter, does it? It's what the orientation is, what beta is. It's the same, because stiffness is way higher than gravity. Similarly, if I'm here, and the way I demonstrate this is, if I have this, what's the natural frequency of, so beta 0, and it's got a low natural frequency. If I do that, they're all the same, pretty much, because you're down here. What's interesting is this intermediate range. And this one especially because it buckles. So when it's oriented up like that, and you put more material in, do this, you get to a point and the frequency is getting smaller and smaller, and it just buckles. The frequency goes to 0. All right, and there's an example of the natural frequencies. It's one of my former PhD students. Now, quite close to the end now. So one of the potential applications of this is vibration isolation. So think of a shock absorber. Now, on your mountain bike, you have springs and a dashboard, and a shock absorber that's sort of been tuned according to a typical person's weight and the speed. What you really want is to be able to tune that more conveniently, stiffness. And so one way you can do that is with a nonlinear spring. And actually what you really want is a soft spring, but something that can hold quite a big load. And so I did some work on vibration isolation elements using these elastic elements. And so for example, this is a video. So watch this. This is my loop, my loop here. It's got a mass, and I'm going to change the frequency of the forcing. So it starts off slow, and it starts to resonate. It goes through resonance. And then when this gets high, this hardly moves at all. So broadly speaking, that's how vibration isolation works. You want to be away from the main resonance, which is the opposite to that sympathetic resonance thing I just handed around. Another example, the offshore drilling. You know, I say here I'm not a fan of offshore drilling. I don't think any of us should be, but a lot of the deepest wells are drilled from floating platforms, drill ships. And this can be 2 or 3 kilometers deep water. And you don't, to be able to drill, you have to be able to have an angle that's fairly sharp for the drill bit to go down. And so there's this buoyant section, so that it sort of goes down more to the seabed vertically. A bit like when you do vacuuming, you know, you hold the lead to keep it out the way. If any of you have ever vacuumed, I don't know. And you can solve all those problems just quite nicely using the Analytical equations. 3D printing, I said I do a lot of that. And then finally, this. So I went back to these polycarbonate strips and I went to 6 inches. This is actually 6 pi, of course, it's a semi-circumference. 6 inches wide, nice and thin pin ends. And then I started to take data. Is that a video? Yes. So you can see, you can decompose that data from the laser into natural frequencies and so on. And then I added some mass, so the thing buckled. And then I put some springiness on those masses, and there's a video. You see what's happening to the natural frequency? sluggish, it's a lot lower. And why did I do that? Back to our answer goes. Because that's what they're doing. So I know it seems like a frivolous example, but the modeling is kind of neat. It is pingent. Right? These ends don't move, but they don't resist rotation at all. They're pins. This is very thin, slender, and it's pretty much a semicircle, isn't it? And it's got a certain width. Look, and he tries to resonate it to get these other goats off because he doesn't like it because he's chained. He's a billy goat. He can't get up there himself because it's too big. Anyway, you can watch that for ages, and they do definitely try and resonate it. And they do push, they bounce, and they know, they sense what the natural frequency is, and they're trying to get it going. And see how much the natural frequency goes down and the large amplitude vibrations? I haven't talked about large amplitude vibrations, and my last slide, though, is this, where we have done some large amplitude vibrations. Everything else has been small amplitude vibrations about highly deformed equilibrium configurations. And all I should say is that the equations governing this are really difficult. And I had to enroll a math friend of mine, Tom Matowski, in order to help solve these equations. So, that's it. Conclusions. Come on time. So, slender structures are unusual because weight competes with elastic stiffness. Almost all engineering, conventional engineering, yeah, we use weight as the loading system, but weight doesn't directly affect the stiffness, if you like, and for slender structures it does. So I found a whole bunch of equilibrium shapes, and of course there could be multiple ones, not unique by any means. First few small vibrations were easily, and that was also based on the shooting method of the underlying PDEs. The experimental results verify the analysis. I mean, they're not difficult experiments necessarily. And I should say that lasers are a great way of taking data from slender structures because you don't touch anything. Lots of different configurations with interesting instability phenomena. And the applications, well, solar sails, vibration isolation, marine lasers, and playful goes. So that's it. Any questions?
Ever encounter situations where modes interact because the ratio is an integer?
That's an interesting question. I could answer that very well. Oh, come on, I've got to. I glossed over this, but I had this idea. Yes. Right. So that model is all based on the fundamental natural frequency, but of course there are lots, right? And the way they come in is through this. So the smallest root, it comes from solving the transcendental equation that comes out from the PE. But there's a whole bunch of natural frequencies, and I thought, well, if you look at the math, it turns out that the fundamental cantilever, the fundamental mode of a cantilever of length L should be the same as the second mode of a cantilever that's 2.5 times longer. So in other words, I printed this, I 3D printed this. So if you pluck this one, the second mode of this should be the same as, I guess it's this one, the fundamental mode of this, right? So that's kind of what you're saying about the sort of interaction between integers. But it didn't work. And the reason it didn't work is because of damping. So it's well known that higher modes damp more quickly. And so, I mean, the damping is related to the sort of curvature of the material, if you like. And so this second mode has higher damping. And so it damps before you can really observe it interacting with that. If there was no damping, I think you could do that.
What about if it was being driven? then the damping might just combine with the forcing, and
Yeah.
you might get some modes that are combination modes.
Yeah, I think you'd all get all sorts of quasi-periodicity, and yeah, there'd be all sorts of interesting things.
So have you worked with the forcing problem at all?
No, but I think the beauty of this is that it's, you pluck one, and that acts as the force for all the others.
Yeah.
Now, yeah, maybe it'd be nice to have some variable control over force and frequency, which you might do in the lab. But this is just a demonstration model, you know? I mean, it doesn't require a
Yeah.
variable speed motor or anything like that.
And sometimes there's like a kind of a resonance of one mode forcing another mode, kind of parametric excitation, but within an autonomous multi-degree freedom system.
Yeah, I know exactly what you're getting at. With this, the trouble with autonomous systems is that they damp,
Yeah.
right? If you can sustain the sort of energy, if you like, the balance between energy dissipation and some input of energy, then you could show all sorts of interesting combination instances. But
Yeah.
Damping is the problem.
And is there a particular theme to how these are arranged? I know that the big one, we just sort of
I
random.
mean, I was trying to make them random. It's actually very difficult to print something that's random. 'Cause, I mean, the brain just likes regular patterns, but I mean, this one, yeah. I mean, so these thicknesses, right? I tried to distribute them random. I didn't want 5 of a certain thickness, 5 of the next. I wanted them because it wouldn't be so convincing if you pluck that and its nearest neighbours vibrating. But this one, you pluck that and its remote neighbours of the same thickness vibrates in the sympathetic resonance. Yeah.
So with this example, have you tried going the other way, that is plucking a long one, but actually not plucking it, push plucking it, so that it's more like the initial conditions for
Yeah,
that?
yeah,
It doesn't work.
it's amazing because what you're saying is, and it's true, it's just the natural frequencies, right? And so, and they could be axial frequencies, they needn't be flexural. So really, any structural component with a whole rich set of natural frequencies, if you excite a natural frequency, it should then excite some other, which could be a completely different mode for a completely different shape, but if it's the same natural frequency. So yeah, we're working on that. Mostly for undergraduate, there's 2 undergraduate projects and they like to 3D print weird shapes.
Pass the gizmo there and I'll try it.
Oh, okay.
It might be possible.
Which one though?
The orange one.
Orange one, yeah.
If that's the one that has, maybe it doesn't have the radar.
Well, that's the thing. You sort of print the lengths and you're stuck with that. It's not like you can tune the lengths, which is to Richard's point, really. In fact, what you're saying is that would be a nice idea if you could change the lengths on the fly. So, because that's like changing the frequency, but you print it.
And a related idea about changing it is if you have something where the frequency is changing as part of the machine, like for example, something spinning up,
Yeah.
then as the spin frequency goes through some of your natural frequencies, you
Critical
get
speeds. I mean, that is definitely a big problem. So any rotor dynamics problem, it's all very well to say, this is your operating speed, 1,000 RPM. But you go from 0 to and if it's a slow spin up, you're actually exciting a whole range of frequencies.
I had a few questions about the bistable loop. So was the Elastica model able to predict both of them, or not?
No, it just predicted the one that sort of naturally grows out of the small loop.
Was that the one that's almost flat on top, or with a large?
Yeah, the flat one.
Flat one.
Yeah. So I wasn't expecting the other one to appear. It just did.
If you view it from the top with a laser or something very accurate, is there any other plane deformation at the center line, or is it?
No, I think it's symmetric about the center line.
would it be a good assumption to treat that strip as inextensible?
I
Just
think
bending?
so. It's that Poisson's effect, anti-plastic bending.
Are the cross sections that, are they, with the snap, it seems like they're deforming. If I cut it at the cross section, maybe one is flat and one is curved up
Yes,
or down.
yes, yeah, yeah.
No more questions. We're serving refreshments in the next room. Let's thank them again, please.